which means we're going to do an example for this test, which is the last one that we'll see. Afterward, I'll break you into your teams, right? So I can do the breakout rooms here. And once you're in the breakout rooms, what I would like is for you to start discussing how to start addressing the research project. I'll answer a couple of questions before, a couple of questions, as many questions as you have before I put you in your breakout rooms. And I'll just give you a couple of pointers as to how you should download your data so that you get to start cleaning it. Okay, so before I start today's class, I'd like to know if there's any other questions. So I said to Sarah, you don't necessarily have to list all the steps number by number. In the same way to Rita, just if you're talking about a parameter, as long as eventually you tell me what the parameter is, what the parameter means, then you're good. But I wanted to see if there were any other questions before we start today's class. Okay, seems like that's a no. So last time we talked about the difference between means between two populations. And this was essentially just us saying, well, if we have two different populations, you could think of these two populations being anything, some qualitative difference, right? So for example, men versus women, or students in the arts and science program versus students in the science program, or you could think of people that have dogs versus people that don't have dogs, or you could think of, anyway, like any kind of thing where you were comparing two given populations, and for which in those two populations, you are trying to estimate a given mean. So for example, you could think of, is there a significant difference in the salary between people that own dogs versus people that don't have dogs, right? So is there a significant difference in the salary? That means you would be comparing the average salary for each one of these two populations, okay? So what we said last time is that any type of test that measures the difference between population means is going to be phrased in terms of the difference of the populations, right? So if I want to show that the means are different, that means that their difference is going to be different than 0. If you want to show that mu1 is larger than mu2, you just have to show that mu1 minus mu2 is larger than 0. And if you want to show that mu1 is smaller than mu2, then you want to show that mu1 minus mu2 is equal to 0. To go back to Rita's question just earlier, in this case, it's particularly important that you specify which mean is which, because depending on which mean is which, what you're showing is different. So for example, I don't know, like Rita could choose mu1 to be the one for people that own dogs, but Sarah then could choose mu1 to be the one for people that don't own dogs. And that means that the test would be slightly different depending on how you choose each of the means to represent a population, right? In one of them, you would be trying to show that the mean is smaller than 0. In the other one, you would try to show that the mean is larger than 0. So you just have to make sure that you have phrased it consistently with your problem, okay? Can I see a yes for everybody that understands this? You know, what the importance between defining the means is and how that can change slightly the type of test that you're conducting. And I know for everybody that does not, goes without saying. Okay. We're at about a half, so I'm going to assume that that's a majority, even though a little shaky on the proportions there. All right, so we developed the following test, which is a test between for the difference between means of populations. We said the assumptions here are that both populations have to be normally distributed and that the samples are independent, which means I don't necessarily, so the salary, for example, of one person in one of my samples should not affect the salary of a person in another, the salary of another person in either one of my samples, right? So the samples should be independent from one another, which is usually what happens unless you're, you know, bundling them by families or stuff like that, which is not something that's going to happen with you. For any of these cases, we said that the null hypothesis, so the basic assumption that we're going to start with is that both means are the same, and then we're going to try to to prove that this is false by providing enough evidence in one direction or another. So that might mean that we want to show that the means are different, or that mu1 is larger than mu2, sorry, or that mu1 is smaller than mu2, right? And depending on that, we're going to use a t-distribution, and we're going to use either the critical value that's above 0, below 0, or the one that splits the alpha into both sides. Be careful when you're evaluating the test statistic in this case, because you'll have to first evaluate S squared by evaluating this term over here, and then you'll have to use that value of S squared in your formula here. Okay, so that's the order in which we're going to do things. So I believe last time I gave you some time to copy this problem. Was this the case? Yeah, I think so. Okay. So what I would like to know first is what are my two populations? So populations. You can either say it on the chat or you can say it out loud. Okay, that's good. So the populations are vegans and omnivores, right? So more specifically, it's going to be Asian postmenopausal women who are vegans versus Asian postmenopausal women who are omnivores, right? So if you want it to be like completely specific, that's how you would have to specify it. For the purpose of this example, the difference that we have between the two populations is simply vegan versus omnivore. So that's how I'm going to focus the problem. Okay, so we have vegans versus omnivores. However, if you were writing a report or if you're trying to conclude at the end of the problem whether there's a difference, you should be specific about the populations that you are thinking about. Okay, so here I'm just being concise so that I know exactly what I'm looking for, but just make sure that you're consistent. Okay, now what I'm trying to determine is if there's a difference or a specific difference between what? What is the mean that I'm interested in? So like if I were to define mu1 and mu2, what would these be? That's right, so it's gonna be the mean cholesterol level in vegans versus omnivores, right? So this is mean cholesterol level in vegans versus the mean cholesterol level in omnivores. Okay, so I'm trying to define everything here so that I have the proper notation, and then I can write every piece of information that I have here by using the notation that I have in this problem, which is population 1 is vegan, population 2 is omnivores, and then all of the notation that I'm going to have to use has to be consistent with this. For example, if you have the mu1 is that for vegans, and that means N1, the sample of vegans, has size 17. The sample average for vegans is equal to 5.05, and the sample standard deviation for vegans is 1.07.
Do we have to write it out like this?
It's useful to write it just so that you don't get confused eventually, because otherwise you might end up switching them at any given point, right? So just make sure that you are consistent with whatever it is that you're showing. And then N2 is going to be equal to 21. X2 is going to be equal to 5.58, and S2 is equal to 1.10. If you want to be fast during a test or something like that, just make sure that you label these with the number that corresponds to them so that you know exactly which one corresponds to which. Okay. So now we're going to try to actually do the test. So we're going to try to perform the hypothesis test, which means that we need to find. First thing is our null hypothesis. And lucky for us, the null hypothesis is always the same for this type of problem, which is that mu1 minus minus mu2 is equal to 0. So I'm going to start with the assumption that both means are the same. And then what I'll end up concluding is, okay, well, if I have enough evidence, I'll be able to conclude that actually vegans have, that actually omnivores have a higher cholesterol level, whereas if not, then that will be that. It seems like they're the same. Okay, so the alternative hypothesis for us is that mu2, so I want to show that mu2, which is the mean cholesterol level for omnivores, is higher, based on the word over here, is higher than mu1, okay? Which means I want to show that 0 is larger than mu1 minus mu2, okay? It's really important that if you have mu1 minus mu2 here, you have mu1 minus mu2 here as well, so that you know exactly what you're trying to consider. Okay, everything has to be written in the same order. So my alternative hypothesis here is that mu1 minus mu2 is actually smaller than 0. Okay, so if I look at the difference, they're going to be smaller than 0. If intuitively you already know to set the alternative hypothesis to be this one, that's completely fine. I'm just trying to give the steps as to how you need to get there. Then you're told that you need to use a significance level of 0.05. Right, so that means this is the significance level we're going to have to use. In step number 4, we have to find the distribution, right? The test statistic. Yes, Lori.
Oh my God, sorry. Is the confidence level and the significance level both are denoted with the alpha?
Yeah, so the confidence level is 1 minus the significance level, right? So here my significance level is 5%. The confidence level for a corresponding, like the corresponding confidence and the corresponding confidence level would be 95%.
Right, but like when we write the little alpha, like we use, if it was like 95% confidence level, we would still write alpha is equal to 0.05. So
yeah. So the alpha is equal to 0.05 is essentially the chopped off area, right? Whatever that means, depending on the context.
Okay, thank you.
Okay. And so at the next step, we need to look at the test statistic that we're going to use, which in this case is x bar 1 minus x bar 2 divided by the square root of S2 times 1 over N1 plus 1 over N2. And this is going to follow a t distribution whose degrees of freedom, so the degrees of freedom here are going to be N1 plus N2 minus 2. Okay. And where S squared is equal to N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared divided by N1 plus N2 minus 2. Okay. All right, so hopefully so far so good. Can I see a yes for everybody that has followed everything so far? Okay. In 5, we're going to have to figure out what the rejection region is, right? Which means that we know that we're going to have to reject the null hypothesis. So we'll reject Yeah. We're going to reject H naught if what? Well, because my alternative hypothesis is that this is smaller than 0, then we're going to reject the null hypothesis if my statistic, test statistic is smaller than t. And here I can start replacing by the values of n1 and n2. So this is 17 plus 21 minus 2, and then alpha. And this has to be negative because it's on the left side, right? So that means I'm going to reject H naught if the t statistic is smaller than t. 17 plus 21 minus 2 is going to be 26. Is that right? Yes, 26. And alpha is 0.05. Okay, now if you go in your table, you're gonna have to look for, yes, Rita.
I don't understand why it's a negative, and why did we write it a negative here, but not a negative when we put the numbers?
Oh, here I'm just missing a negative, but it's a negative because you're trying to show that the values are extremely low, right? Which means that they're lower than usual, and so that means that you need to show it from this side of the distribution, which means that you need to chop off the 5% here, not from the top of the distribution, but from the bottom part of the distribution.
Oh, okay.
Yes, Sarah.
Okay, wait. Did you say the degrees of freedom are 26?
Yes.
Okay, I got 36. Is that possible?
That's perfectly possible. Absolutely, 36. Yeah, 36. Thank you. Yeah, I can't add. All right. Now that means that in our table here, we're going to have to look for the column with 95%, right? Because it's the one that chops the top 5%. And then we're going to have to look for the row that corresponds to 36. And we can keep looking here, and you're going to see that there's no row exactly fitting at 36, which means we're going to have to use the one for 35, which is the closest one. Okay. The reason for that is that depending on the size of the sample, you're always going to get values that are, so you might get values that are between other values, which means that once again, as in our table as in our Z table, we'll just have to find the intermediate value. And Sarah, you have a question?
Yeah, like I'm a bit confused as to why we're using 95, because I thought in our other test where we used the t table, even when it was like an alpha of 0.05, we still use 97.5.
Right. That's if we were looking for a difference. But in this case, we're trying to show that we're not trying to show that the means are different. We're trying to show that that one of the means is larger than the other, which means that this is a one-tailed test and not a two-tailed test, right? So we'll have enough evidence if I'm on the lower side of the distribution. If you were trying to look for a difference, you need enough evidence. That means on either side of the distribution, which is why you have to divide it by 2.
Yes, right. Okay, sorry. That was just a moment of.
Oh, that's a good question. That's good. And so for 36, that means that here we're going to reject if this row, this column, which means this value, 1.69. Okay, so we will reject H naught if t is smaller than 1.69, but of course this is on the left side of the distribution, which means negative 1.69. Okay, and now that we have that, we know that it is negative 1.69. That means we're going to have to find the actual test statistic for our sample, and then try to see, where it lies with respect to this number. So for us, that means we're going to do t is equal to x bar 1, which is 5.05 minus 5.58 divided by the square root of s squared, which I'm going to evaluate on the sidelines here, times 1 over 21 plus 1 over 17. 1 over 17, 1 over 29. I just want to write it in order. 21. And s squared is obtained as n1 minus 1, that's going to be 16 times s1 squared, so 1.07 squared, plus 21 minus 1, which is 20 times 1.10 squared, divided by 16 plus 20, which is 36. Now, if you evaluate this, hopefully you'll find the same value as me. Correct me if you don't find the same thing. I found 1.1741.
Why is it 36? Because aren't we supposed to use just the n1 and n2 denominator and not like n1 minus 1?
n1 plus n2 minus 2, which is the same as n1 minus 1 plus n2 minus 1, right? We're just collected.
So sorry, I was looking at the wrong formula.
Don't worry, there's not going to be, there's not that much lecture time left. So the iPad will survive until the end of today's class. So yeah, here we have 1.
I'm not sure if it's a big difference, but I got 1.18, but I might be mistaken.
1.18. Okay, just gonna verify it here.
Yeah, I got 1.18 too, but I don't know if I rounded it. Wait. Oh yeah, I got 1.18106.
1.10 divided by 36. It's perfectly possible. Of course, I made a mistake somewhere. 1 divided by.
Also, I have a question.
1.1810.
From when we were looking at like how we decide to just take the 35th degree of freedom instead of like doing the average,
because
like,
it's not exactly between.
But
right?
like I calculated it. Like I found out exactly what was 36 because like if you like that makes a difference because if I take the 35th then like it ends up being one thing, but if I take the 36 it ends up being something else.
Yeah, so if you take the 36th one, what value do you find?
One second, I just deleted it.
It should be about like 1.689, right? So chances are that you're not going to fall exactly at the value that's like in there. And therefore, for the most part, the approximation is going to be just fine because chances are you're not going to be like at that boundary where like if you make like a tiny little rounding difference, you make it in or you make it out. Usually the result is a little bit further away so that even if you change the boundary by just a tiny bit, your result is going to be on the same side of the distribution. Okay,
so like no matter what, I don't need to, like I just pick whatever degree of freedom is closest.
Yeah, so you can definitely estimate it, but in an exam, it will be enough to look for the nearest value.
Okay.
And because you're going to be given this table during the exam, then you might as well just work with this because it's always possible. You could also like, you know, use the internet and that will give you the specific value. You could also use R and that will give you the specific value. And like, there's always ways to get exactly the value that you want, but there's really no need to do that because I'm just asking for like a general idea of what's kind of going on here. Okay, so Michelle, when you when looking for T36, why 35? Oh, okay, sorry. Yeah, I was just answering that question. Good. And Lori.
Oh no, I'm okay. You answered my question too.
Oh, all right. Well, I answered a bunch of questions without realizing it. I wish everything was as easy as that. So then what do we have? Oh, okay, the value. Okay, that means I have to reevaluate mine because I don't know what mistake I made, but I didn't have the right one. So here we go. We have 5.05 minus 5.58 divided by the square root of 1.1810 times 1 over 17 plus 1 over 21. And that's equal to negative 1.49. Okay, 49.5 because we have 3 numbers after the decimal in t, so I'm just going to use 3 numbers after the comma here. All right. The one piece of advice here is that when you're evaluating the t value here, make sure that you enter everything in the calculator at the same time. That's thing number 1, to avoid rounding mistakes. Thing number 2, because you're going to have to write everything in your calculator at the same time, be very wary of brackets. Okay, so you need to put the brackets, like in your calculator, you would have to put brackets around this, you would have to put brackets around this, and you would have to put brackets around this. Okay, so just make sure that you put all the brackets so that you don't have any mistakes once you're evaluating this. Now we have that the value for our sample was t, which was negative 1.495. And that means in 7 that we failed to reject H0, right? We failed to reject H0 because we didn't get a result that was as extreme as we expected. What we had said is we will have enough evidence to say that the cholesterol level for omnivores is larger than that for vegans if I get a result that is in this region. So this is negative 1.69. If I get something around here, then I will be able to reject H0. This will mean that omnivores actually have cholesterol levels that are higher than those of vegans. But from here, what I got was a result that was maybe somewhere around there. Right? Still negative, but not as extreme as I expected it to be. That means that I don't have a value that is as extreme as I required it to be in order to reject the null hypothesis. Can I please see a yes for everybody that understands this and a no for everybody that does not? All right. Again, about half the class, which I'm assuming means a lot of you are still taking notes. So another comment that I want to make is, suppose that I asked you to determine something about the p-value. I won't ask you to evaluate the p-value in this case, but I could ask you, what can you say about the p-value? Okay, so what could we about the p-value? I'll write down the full conclusion in a second, but for now I just want to think in terms of probability. What can I say about the p-value? What we said about, so when we defined a p-value, we said that was the probability that I get a result as extreme or more extreme than the one that my sample produced, right? What is the probability that I had gotten something as extreme or more extreme than the one that my sample produced? Now, you can use several arguments. First, you can look at the distribution here, and you can realize that this p-value is going to be the shaded part in blue, which is going to be larger than the area that was shaded in black, right? So you have that the p-value is larger than the area that was shaded in black, which means 0.05. Now, what does this mean? Well, it means that under my null hypothesis, assuming that these two were true, assuming that these two were the same, assuming that the cholesterol levels between the two populations were equal, this would mean that I would get a result as extreme or more extreme than the one that I had, like a difference as extreme or more extreme than the one that I had in more than 5% of the cases. right? This means that the result that I got is not in the most extreme 5% of the cases because it happens more frequently than 5%. And therefore, that's why I can't reject the null hypothesis. Does this make sense? Can I see a yes? And here I'll require 3/4 majority. So that means I have 29 people. I need about 17 to vote yes.
Can you write it down so maybe like I can process it?
I'll write it down. I'll write it down. I just want to know if you understand the gist of it. Would you like me to re-explain?
I need to like see it before I can tell you if I understand.
Okay. So once again, I'll re-explain, then I'll write it down. Because I had a result that wasn't as extreme, that means that if I look at just the shape that I have over here, I know that the area, the rejection area, which is the part that I had shaded in black, this was 5%. And what I had said is, if my result is in the extreme 5%, then I will reject my null hypothesis, right? That was my condition. Now, we ended up concluding that we can't reject the null hypothesis, which means that I didn't get as extreme a result. This means that under the null hypothesis, my result is more likely than 5%, which was the probability that I had associated with it, to occur. So if the means are actually equal to begin with, then I will observe a result as extreme or more extreme than mine in more than 5% of the cases, right? So with a probability of more than 5%, I will observe a result like mine, which means that my result isn't as unlikely as I would like it to be to prove that my original hypothesis is false, right? So I didn't have extreme enough evidence to conclude that the null hypothesis is false, all right? So I'm going to give the final conclusion to the problem, and then I'll give the interpretation of the p-value. Okay, so first we failed to reject the null hypothesis, which means that there is not enough evidence with a significance level of 0.05 to suggest that cholesterol levels, that the cholesterol level for omnivores is higher than the cholesterol level for vegans. Okay, then in the p-value over here, I have that the p-value is going to be larger than 0.05 because we said we would reject H0 if it was in the most extreme 5%, which is alpha here. So depending on the alpha, you would have the most extreme 1% or 5% or 10%, depending on the context. It was in the most extreme 5% of the values, assuming H0 was true. Okay. Now, because we didn't reject, this null hypothesis, that must mean that we were not in the most extreme 5%. 5%, which means that the p-value which is the same as the probability of getting a result as extreme or more extreme than the one in our sample So the probability of getting a result as extreme or more extreme than the one in our sample must have been larger than 5% or larger than alpha in general, because we didn't end up rejecting, right? It wasn't as unlikely as I wanted it to be. This means that, okay, so before I make the last comment that I want to make today, could I see now a yes on the participants booth for everybody that understands this, and a no for everybody that does not? And Sarah, you have a question.
Yes, of course. I don't get the part of getting a result that's more extreme than the one in our sample.
Okay, so in our sample, we're saying, I'm going to conclude that there is I'm going to conclude that the cholesterol level for omnivores is larger than the cholesterol level for vegans if the estimator for T, so if our test statistic is in the most extreme 5%, right, in the lowest 5%. That means that if I get a result that is in the lowest 5%, then I can say, oh, actually my original hypothesis doesn't seem to have been true. Okay? However, if I assume that H0 is true and I get a result that is not in that extreme 5%, that means that the probability that I got something beyond that, well, because I'm not in the extreme 5%, because I'm not in the bottom 5% of the cases, then that means that there must be more chances than 5% of getting such an extreme result. Okay, the idea being that if you have, for example, here the distribution. Now, what we said is we're going to reject if I'm in the most extreme 5%. Okay, that means that I will reject. So if I'm in this part, I will reject H0. I will say my result is too extreme to be explained by H0. But if I get the result here, I'm going to say, oh, I don't have enough evidence to suggest that H0 is not true because I don't have an extreme enough result. Why is this result not extreme enough? Because this result, this one over here, is a little bit more likely to occur under the null hypothesis, right? So under the null hypothesis, I know that most of the times I should expect my results to be somewhere around here, right? So I should expect my t statistic. If the null hypothesis is true, I should expect my t statistic to be somewhere around here or here or here most of the time. Some of the times it's going to be really high, some of the times it's going to be really low, okay? But if I look at the probability of being more extreme than mine, right? If I have a result that is very extreme, like this one, then the probability of being as extreme or more extreme than this will be this area over here. Right? Because I have such an extreme result, that probability is very small, right? Because I had something that was very high, so the very low, so the probability of even being lower than that would be really small. Right? So under my null hypothesis, the probability that you get something even lower than the value that you got is going to be very tiny. On the other hand, if I get a result like this one, well, this is closer to what I should have expected, right? Which means that in this case, I would expect that the probability of getting a result lower than that, because this is not such an extreme result, the probability of getting something even lower, well, it's not going to be that small. It's going to be quite likely that I get a result that is even below this, which corresponds to this area being, well, not that small, right? Because I don't have something that's so far out in the distribution, then getting something even after that is not going to be that large. That more or less makes sense. So this brings me to the last conclusion that I want to make here, which is that if the p-value, so suppose that in a given sample, I reject H0. That means that my result is in the most extreme alpha percent. Okay, so in this case, I'm just going to do it with alpha so that it applies to every single possible case. If I reject the null hypothesis, that means that I must be in the most extreme alpha percent, which means that my p-value must be smaller than alpha. Why? Because the probability of getting something as extreme or more extreme as what I got in my sample has to be smaller than that threshold I set. However, if I fail to reject H0, if I fail to reject H0, that means that the p-value is going to be larger than alpha. Okay. Once again, if I do it in this case with the one-sided test, that means, let's say this is my rejection region. And so I have the distribution, my rejection region is here. And I know that the area here is going to be alpha. Well, if I reject H0, that means that I must be in the rejection region, which means that the probability of being even further than that has to be smaller than alpha. Whereas if I have that I fail to reject the null hypothesis, then that means that my result must not be that extreme, which means that getting a result as extreme or more than that must be larger than alpha. Okay, so it's just a way of, it's another way of understanding hypothesis tests. All right, so I'll let you think about that. Might take a little bit of time. But if you have any questions, of course, you can let me know.